Hey there again, class. Welcome to Chapter 2, Section 2, where we'll be discussing a little bit about statistics and models. So, as we get started, we're going to just kind of cover what we're going to be going over. Biggest things here is we're going to be talking about how scientists use statistics, and we're talking about how we talk about averages and distribution and probability. So, we're going to go through this and hopefully, this is something you have further questions about or need any more help with. Please come see me. Don't get stuck on this, but it is extremely important to understand because statistics and models are really what hold science together. They are the glue that makes science science and opinion. So let's continue. So we're going to talk about understanding the news, models, graphical models, conceptual models, and mathematical models. And we're going to be doing a lab this week where we're going to make a model of the school and just kind of show, how we would bring that to scale and how scientists and other people use models, not just of a physical nature, but sometimes also of a conceptual nature. You see that term a lot in the news, and they start talking about models that predict hurricanes and different weather patterns and things of that nature. So models, the important thing to understand is that models are something that are framed or generated around something that which has already happened or already exists, whether it already be existing in the physical or in someone's mind. For example, the Tesla truck that just came out, before that was actually produced, there was a conceptual model of that truck, and actually the model was in existence before the real truck that people are now driving around and spending, $130,000 of their hard-earned money on. So we got to talk about what's the difference between the responsible use of statistics and the misleading use of statistics. We talked a little bit about this in class. If you remember a couple weeks ago, we talked about how some of the old tobacco companies, when they were doing research data, they were twisting and contorting statistics for their favor to show or to attempt to show and to demonstrate that tobacco wasn't as harmful maybe as it is. And you see this a lot. You really see it anytime you're at the grocery store and you see the words like organic or any of those things that say like fat reduced or any of that. What's happening is that those words can't be on a box until they've been put through some kind of lab testing. And what's happening is that manufacturer or that marketing company or whoever's coming up with that is then perhaps twisting the data to say, hey, this is fat reduced. So it's up to you, the consumer, and then in that instance, you really kind of become a scientist per se, to say, okay, I'm being given these data and the statistics. How do I look at that and examine it and determine whether or not it is everything that they're cracking it up to be? So we're going to talk about how scientists use statistics, explain why the size of a statistical sample is important. For example, if I had a study and I said, hey, these certain people are subject to this condition, well, if I only have a sample size of 2 people, obviously it wouldn't take a real genius to determine, well, you maybe didn't test enough people, or maybe that's inconclusive. Maybe you need to go out and sample more people. To talk about the different types of models commonly used and to explain the relationship between probability and risk. So explain the importance of conceptual models and mathematical models. So let's get into it. So statistics are really, just to understand, this is a key term, the collection and classification of data that exists in the form of numbers. For example, how tall you are, how much you weigh, how old you are. Those are statistics. And if you are now standing in a room full of people, imagine you're in this room full of 500 people. If you went around and you asked everybody their age, okay, now you would have a sampling of people and you could take all those ages and say, okay, the average age of the person in this room is this. Or we have a range from 2 years old to 100 years old or what have you. So these are all pieces or all examples of statistics in their simplest form, and they rely on those because, again, we talked about relativity. We talked about how you just can't say short, tall, you can't say skinny or fat, you can't say old, young. You got to be able to quantify that in some way. You got to be able to say, okay, this is how we do it. These are when we come back to what we talked about, metrics. We start talking about weight. We start talking about gallons. We start talking about however it is, whatever unit by which we buy things or measure things or look at things. So imagine if you're driving a car, you got pulled over, and the police officer said, you were driving fast, so I'm going to give you a ticket. No, you would want to say, well, wait a minute, how fast was I going? That's a metric. And he would say maybe you're going 50, and you would want to say, okay, well, what was the speed limit? 35. Okay, now we have some quantifiable data that says that perhaps you were or were not speeding. And so that's why these are important, because really what happens is statistics is what keeps people honest and what keeps data versus just a bunch of opinion or conjecture. So statistics, it's actually a branch of mathematics, so we're going to be doing a little bit of math this week. Not a ton, because I'm not a math person, so we'll ease up on that. But we're going to talk about populations. Scientists use statistics to describe statistical populations. For example, when we were talking about first world countries, second world countries, developing and developed, we have to know, hey, if we have X amount of people in a country, we start talking about the life expectancies. We start talking about health data, statistics. We got to start being able to look at pools of people and populations, and to determine what is the relationship, not only by where they live, but also by what's happening to them and the effects of their environment. So we look at averages. That's a big part of science, is to look at averages, but we also got to look at individual characteristics. The mean, here's a key term. The mean is the number obtained by adding up. What does that sound like? And dividing the sum by the number of individuals. Mean, think of it as an average. So when you're talking about mean, you're talking about averages. So the mean provides a single numeric measure for a population, so it allows easy comparison. So for example, if I'm trying to talk about 20 people and they're all pretty relatively the same, versus me having to break out the specifics of every one of those people, I'm going to come up with a mean or an average so that I can classify them together, because really maybe any differences are going to be minimal, so the data is still viable, but it also saves time. So talk about distribution. It's the relative arrangement of members in a population, also known as a graph. So if you looked at bar graphs, pie graphs, or whatever, that's called the distribution. That's saying pretty much where do you fall in the numbers. Think about it like this. Distribution would be like if you're in a classroom full of, say, 25, 30 kids, and your grade is an 80, okay, and everybody else's grade is, either higher or lower, and if you were to itemize those one by one, where do you fall in that ranking? So that's distribution. And so we look at the heights of people, we look at from different bell-shaped curves, we look at all different ways to look at data and how it can be illustrated, how it can be distributed. And really what it does is when you distribute data, it paints a picture that helps our brains and our eyes and our senses understand what is maybe happening. And so here's a good example of that. If we look at the size distribution of dwarf wedge mussels, this is an ocean creature, and you can see that they go from 15 to 50, but obviously the length is primarily up in that 30-ish, 35 area. So this kind of helps you get an idea. So if you saw now, right, a distribution, or if you saw a dwarf wedge mussel, you would think its length would be what in millimeters? Approximately between 30-35 based upon this data. So that also lends itself into probability. Probability is the likelihood that a possible future event will occur given certain instance in the event. We talked about that. Remember, I kind of jokingly talked about a Harvard study that said, hey, probability says that one who stands in the middle of the street is more likely to be run over by a bus. That's probability. Probability says out of how many things happening, what are the odds that it could happen to you? Think about rolling the dice. If I have a six-sided dice and I roll it one time, what is the probable odds that that dice is going to land on three? Well, it's going to be what, 1 in 6, because you have the six sides, and so there's probability that takes place there, and we're going to talk about what is probability, and pretty much talk about, because probability comes from what's possible, also depends on how many times it goes around. For example, you see probability when you buy lottery tickets, you see probability everywhere, so it's a pretty interesting thing to understand. So we'll dig into that a little bit. And it's usually expressed in a number between 0 and 1 as written. So we'll talk about, because 1 obviously would be 100, 0 would be, the lowest end of that probability. There's also got to be a large enough sample size in order to attain accurate results. Again, we talked about playing the lottery. You can know the probability because a lot of people play the lottery. So we know that millions of people buy tickets a day, millions of people play those games. So, and we see how many people win. So that it's because of that huge data sampling that we're able to get a good probability and we're able to get a good idea. So pretty much when you're thinking of probability, the more data you have, the more accurate your probability prediction can be. If you're a sports fan, hypothetically, like for example, baseball is really a lot about probability and statistics. That you see that batting averages. A batting average is a probability. So when you see like a batting average of like 307, that's telling you that .307, that's saying that 3 out of 10 times that person goes up to bat, they're going to get on base. So understanding the news. The news contains samples every day. For example, a reporter might say, again, in this instance, a study shows that forest fires increase air population. That's a study, that's a statistic. But now we had to start looking at, this could lead you to gather data and graphics. So when you look at the news and you look at the information that's given to you, this is when we start going back into that scientific mindset. You got to start asking some questions: why, when, how, and does that seem right? Does that seem like something that I'm comfortable with? Is that information that I can buy into? And even if you can, you want to test it. And this is when experimentation comes into play. So data, probability, and all these are the fruit of experimentation and observation. So in paying attention, it'll just make you really a better consumer of information. So especially in this day and age, you and me and myself, and we're inundated with information, but understanding it and being able to, that word we use, discern it, is extremely critical and extremely important. And so we start thinking about risk. Risk is the probability of an unwanted outcome. So I can start thinking about, is what I'm doing, does it bring about an unwanted or unmerited risk? For example, if you're someone who plays the stock market, you put your money into a stock, but what's the risk of you lose everything, in contrary to the fact that your original desire was to win, or not win, but earn a bunch more money on that stock. So where there's probability on one side, there's always risk on another. So remember, when you start talking about probability, there's always risk. That's called gambling. So for example, that lottery ticket talked about, the probability says you can win, but there's also a probability that you won't. So that's the risk. You wanted to, but you don't. And so people often worry about, all these different things, big spills and all these, like we talked about. In Florida, we still pay a tax from an old oil spill. But think about, like, when you get old enough, you buy a car and you put all your money into it, what's the likelihood, maybe the risk that it breaks down and all your money's gone and you don't have a car? So there's lots of risk. We consider the most important risk we consider, obviously, is the risk of death or physical destruction. So much of what we do keeps us from doing the things that we don't normally do. Like, for example, if you have a fear of flying, people who say, hey, I'm not going to smoke or do drugs, all that's really comes from a fear of risk and saying, what is the negative outcome of that action? So models are patterns, plans, representations, or descriptions. And so, like, for example, using that whole thing of, hey, don't smoke or get on an airplane. we look at models and we say, well, okay, well, what could be the risk? We look at the models and say, you know, you hear all the time, well, people say that airplanes are safer than cars. Okay, that's a model that's being used. So the model would say, if I get on this plane, I'm actually safer on the plane going from here to wherever than I am be if I were to actually driving based upon the model that was developed through data and statistics. So, and we use that in a lot of different ways. To learn about our environment, to predict our environment, to change maybe the course of behavior that we're doing now. Obviously, think of models as almost like a crystal ball, if you will. And those are just a few kinds of models. And if we go on, we have what are called physical models. Think of a physical model simply like a toy store, or the hobby store. You go and you buy a model of a Corvette or what have you, and it'll show you sometimes that it's like 1/16 to scale. So that says that if you were to blow that up by 16 times, it's going to be the size of an actual authentic replication of the model from which it's based. So we use those a lot too in science. So for example, if you've ever been in a biology class and they have a human brain or a skeleton, that's a model of that actual function, so that way you obviously can have the usage to learn about the real thing without having to destroy the real thing. So that's a physical model, and the three-dimensional, you can touch, taste, smell, feel, whatever, that they closely resemble the object that they represent. And again, usually they're smaller or larger. For example, if you're looking at a model of a human eye, it's usually going to be much bigger so that you can see more of the detail more precisely and easier. And they're great for teaching and things of that nature. So one of the most famous ones, again, as we've seen, is the structure of DNA. And so we'll take a look at one of those this week and get an idea as to what that looks like. This is why we looked at some of the microscopes, so we can start to see what that looks like at microscopic level. Then we'll look at, okay, let's bring that to life and show you in a model replication. So, and then we have graphical models. Again, coming back to the hurricane models, we're not going to spend a lot of time on that, but those graphical models will just predict based upon future, past, and even present information what they think the future might be, and that goes on to conceptual as well. So explanations, a graphical or conceptual model shows how a system work is organized. Flow charts, things of that nature, are all ideas of conceptual models. That way it kind of relates to another person how something is supposed to happen, or the cause and effect nature of different things, and it kind of puts that on paper so it's easier for everybody to understand. Kind of looks like this. Mercury released from the air goes in the air, the soil exchanges, and it affects fish, crops, people. And as you can see, looking at that conceptual model, that's a much more powerful tool to explain how that happens versus just trying to verbally explain it to somebody. It really brings that information to life. So that's what a conceptual model is for. And it just, right back here, mathematical models are where we just take equations and work and see how processes work. So I could spend a lot of time on mathematical models, but we will need to understand them. Again, this is what they start talking about, variables that affect weather. This is where they might say, hey, based upon previous data, we predict that the rainfall will be this in the given area, climate, whatever, what have you. And so they're not always right. Mathematical models can change because mathematical models don't take into consideration external variables. So, like, for example, if I looked at the historic humidity patterns in Arizona, for example, those aren't going to be accurate most likely because of the change in Arizona of population density and the proliferation of non-native plant and development in that area is actually changing some of those models. So people are the ones who interpret data. That's important. Understanding that when you're looking at mathematical data, you also have to understand it is up to the one who interprets it. So if it's been interpreted poorly, then it's going to obviously be a problem. So, but the long and the short is that models are important and statistics are important because, again, these are what the glue that holds science together. And these are going to be your vocab words for this section for the week. We'll get those posted. And if you have any questions, please feel free to come see me. Would love to help you if you're getting stuck.